Okay, the next example we have here is example 5. Given the region enclosed by y equals 2x minus x squared, x equals 0, and y equals 1, determine the volume of the solid if it's generated by being rotated about the x-axis, y equals 1, and the y-axis. So here, this problem, we can think of this as like a three-part problem. We just have three different axes of rotation. And for this problem, instead of determining the actual volume, I'm just going to set up the integrals. I think that would probably be the easiest. So let's go ahead and do that. So first, let's sketch our region, because that will be the same regardless of what our axis of rotation is. So we'll draw that. So x-axis, y-axis. This polynomial right here, we can write this as, of course, y equals x times 2 minus x. So this is a parabola that opens down with an x-intercept of 2 and 0. So let's say this is 2. Then 1 is like about right in the middle there. So let's just say we have something like this. Something like that. We can move this around a little bit so it looks a little bit nicer. There we are. So there's the one graph. We've got x equals 0. X equals 0 is just the y-axis itself, and y equals 1. So we have to figure out, where do we draw y equals 1? Do we draw it up here? Do we draw it right there? Or do we draw it below here? So we really have to figure out, what is this y value? So we know this is x equals 1. So this value here would be whatever we get when we plug in 1 into the function, which would be, so this would be y of 1 would be 1 times 2 minus 1, which is 1. So there's y equals 1. So y equals 1 actually goes right through this. So let's go ahead and draw that real quick. And we'll just line this up to make it look nice. Okay. All right, so now what we want to do is figure out how do we set up this, or let's identify the region now. So the region here is using all three of these, the parabola, the y-axis, and the horizontal line as the region. So that encloses this outlined in blue region. That is our region that we'll rotate. So to do this, let's start with part 1. So for part 1, we want to rotate about the x-axis. So if we're going around the x-axis, rotate about the x-axis, then we're rotating here, in which case we want to draw a line segment that's perpendicular to the x-axis. That's our radius. So we can think about drawing a line upward from our axis of rotation to measure our inner and outer radii. You can see that there is this gap below the blue. So this gap is what's going to cause the washer. So this is a washer. So this would be our inner radius. So our inner radius appears to be the y value for this parabola. And then the outer radius appears to be y equals 1. So this is a washer, so the volume would be pi times the integral from a to b, the outer radius squared minus the inner radius squared. And then since we're rotating about the x-axis, dx for discs and washers. So our a to b is 0 and 1 respectively. Our inner radius, we just said, was the parabola, so 2x minus x squared. And our outer radius is the line y equals 1. So using this information, guess I can put some commas in here. Using all of these pieces, we can figure out the volume. So the volume V, therefore, is pi times the integral from 0 to 1 of the outer radius squared, so 1 squared minus the inner radius squared. The inner radius is 2x minus x squared. All right. So moving on to the next one. For 2, we are going to rotate about what? Y equals 1. So again, this is a horizontal axis. So we are again going to use exactly the same setup here. We've got the integral from a to b of outer squared minus inner squared. Oops, I just realized I wrote my parenthesis on the wrong side. Should be squared. My apologies. So I quickly just, this square I actually wrote on the outside. This should be really here. This was correct here though. Okay. So same thing. Our a and b are the same as the previous time, so from 0 to 1. Our inner radius, though, what's that going to be? Well, since we are rotating from this axis, the inner radius itself, well, do you notice how this isn't actually a washer now? The inner radius is technically 0 because the axis of rotation touches the region. So this is really a disk, not a washer. We wrote this washer down. So if you really want to force it, you can say that it's 0 in this case here. Well, I'm sorry, it's not 0. It is the distance. Actually, yes, that is true. The distance is 0. I'm sorry. The distance is 0. That is true. Because we're measuring the distance. Well, our region begins at that inner radius, and the distance we travel to get to this line is 0. So this is really supposed to be a disk. So if we just modify this, a disk, not a washer, has a really similar format, and that is it's V. So pi times the volume V equals pi times the integral from a to b, but instead of having 2 radii, we're just going to have a single radius. So this is just r squared dx in this case. So whether we want to treat it as a washer, in this case, you can see how a washer then would reduce to a disk, because our inner radius would just become 0, so we would subtract 0 and we just have the single radius. So we'll just change this out, and we will talk only about a single radius, since it's a disk, not a washer. So in this case, the r from this formula for a disk is the distance from your axis of rotation to your radius, to your outer boundary here. Well, we know that this full distance is 1, and we know that this distance here is just the y value since it's tethered to the x-axis. So this distance here must be the big distance minus the little distance. So there should be 1 minus y. We need things written in terms of x, so this would be 1 minus, and then on this curve, the relationship between x and y is given by this function. So we just have to swap out y for 2x minus x squared. Okay. So our volume of the solid, V, becomes pi times the integral from 0 to 1 radius, which is 1 minus 2x plus x squared if we distribute, radius squared dx. Okay. Part 3. We want to take a look at rotating about the y-axis. So if we take this same region here and rotate about the y-axis, we have a slightly more substantial change. And that is, instead of drawing a line segment perpendicular to our axis of rotation, we still do that, but instead of it being perpendicular to the x-axis, it must be perpendicular to the y-axis since we are now rotating about the y-axis. So if we draw this line segment out, this is at some arbitrary height y, so this distance here is some x. So our radius is actually equal to x. So for the rotating with the y-axis using discs or washers, this is the integral, so pi times the integral from a to b, of our radius squared dy, since we are rotating about a vertical axis. So this is the slight complication, is that we need to integrate with respect to y instead of x. And our a is the lowest y value, which is 0. B is the largest y value to which our region extends, so 1. So our region is still 0 to 1, just like before. But in this case, our radius, again, this is not a washer because we are rotating about the y-axis, and our region here actually touches the y-axis everywhere. So it begins there. So there's no gap. So this is a disk, not a washer. So we have a single radius, and that radius happens to be x, because we always measure our radius from the axis of rotation. And whenever you measure something that's tethered or begins at or goes to the y-axis here, we can call that an x. But we need this in terms of y. So on this curve, the relationship between x and y is y equals 2x minus x squared. So we have to solve this equation for x, which is not terribly difficult to do, but it is slightly involved. So to do this, what we can do is I'm just going to move the x squared to the other side, just so I have my x squared term positive. So I'm going to move all my x's to the other side, and then I'm going to go ahead and subtract y. I really just want my leading term to be positive 1, so I did that switcheroo. So now what we can do is complete the square. So I can add 1 to each side, which completes the square. So this becomes x minus 1. Remember, for the method of completing the square, the thing that you add here is half of this coefficient squared. So grab the coefficient, divide it by 2, then square it. So we get -1 squared, which is positive 1. So I'm adding 1 to each side. Then this collapses down into x minus 1 in this case. It collapses down into half of this number. Okay, so then we can solve this by taking the square root. So I'll just come up here, and this would be x minus 1 equals plus or minus the square root of 1 minus y. So x is 1 plus or minus the square root of 1 minus y. So this creates two branches, because this parabola, this parabola here, it is a function of x because it passes the vertical line test. If I strike a vertical line, it only hits the graph once. So this means if I plug in a single x value, just pick an x value, then there's exactly one y value. That's what it means. If you plug in this x value, that corresponds to this y value. It's not a function of y, however, because if I plug in a single y value, there are actually two outputs. So there's two outputs for this one input of y. So there's two x values, two outputs for this single input. So we can't say that this graph is a function of y. And because of that, this is exactly y. It's not, algebraically. It's because if we plug in one value of y, it's going to be used twice, in a sense. We'll figure out the square root number, and then we're going to add it for one of the x values and subtract it for the other x value. So which branch do we pick here? Well, we'd have to pick the branch, each of these two terms, the positive root and the negative root. These are the two branches of this function. Well, we want the minus because we want something that is less than 1, right? If the x value is 1, think of that being right here. So then to the right of this, that's x value is larger than 1. And if we're over here, which is where we want to be, then we have x values less than 1. So we actually want the negative root. So we'll take the negative root. Okay. So this radius being equal to x, if we need it in terms of y, which we do, we had to do a little bit of algebra to get that into the format we wanted. So it's not great. So setting this up, the volume, v, is pi times the integral from 0 to 1, and then this squared. dy. There is an easier way to rotate about the y-axis without having to do all this algebraic solving for the inverse, one of the inverse branches, and that is using a method called the shell method, which will be talked about in the next video, which is where we actually interpret this as like a little, the side of a cylinder being rotated about the axis that way, in which case we don't have to do anything that crazy.